unitary entity. Very good.
The speaker is Matteo from UT Austin. Pseudorandomness and quantum thermalization.
Right. Yeah, thank you so much for to the organizers for putting together this amazing workshop. It's been a really exciting 3 days, and thanks everyone for sticking around till the very end. I promise it'll be pretty light, not too many equations. Okay, so I will be talking about some ideas that follow very nicely from the talks we've heard about today about pseudorandomness, and I will really try to find some precise connections to quantum thermalization, things we've heard about in the first couple of days. So we've already had some very good introductions to the general topic of thermalization. By now, we're all experts, so I'm going to go very fast. But I want to emphasize this aspect of thermalization, which is that it has to do with the emergence of randomness and the loss of information somehow. Somehow, when we approach thermodynamic equilibrium, we have to witness some loss of information from a precise description of a state of a system down to some statistical ensemble of possible states that involves some ignorance. Okay, so the precise mechanism by which this happens is a little complicated. We've already heard from Soon about various subtleties in coarse graining and so on in classical systems, but it's underpinned by these kinds of concepts like chaos and ergodicity. That mean that we don't want to describe individual states of our system, but rather ensembles of random states. In the quantum world, we don't have these processes of dynamical chaos and ergodicity in the same way. It's a bit different, but we have, even though our evolution is linear and unitary, so it doesn't destroy any information, there's no information loss, we still have a mechanism that propagates this information into collective degrees of freedom of our many-body system in such a way that if we focus on a local subsystem, then information can be shared non-locally and locally inaccessible. Okay, so even though our overall many-body state is pure and has complete information on the state, the behavior of local subsystems can look stochastic. Okay, it can be described by a mixed state, and the emergence of this mixedness describes this sort of appearance of randomness. Okay, even though there's no randomness, we have this appearance of stochastic behavior, and this is very reminiscent of this concept of pseudorandomness that we've heard before. Okay, so in this talk, I want to zero in on a couple of ideas that I've been interested in lately, as well as many others. The first part of the talk will be about this concept called thermalization, which is about the emergence of universal pseudorandom distributions of wave functions from quantum many-body systems subject to partial measurements. So this is one of those post-measurement phenomena that Ehud talked about the other day. And in the second part of the talk, I will instead discuss a concept that we labeled pseudo-thermalization. I'll tell you what it is. But it's about spoofing or reproducing all of the efficiently testable predictions of thermal equilibrium with a relatively small amount of entanglement. And of course, this builds on these recent developments in pseudorandomness and pseudoentanglement. Okay, so let me start with part one, and feel free to interrupt me as I go. So, as I was saying, the emergence of thermodynamic equilibrium in quantum systems has to do with the spreading of information into these collective degrees of freedom in isolated systems. And this is not just a theory idea, but it's now becoming increasingly testable in laboratory settings, in quantum computers and quantum simulators. There, the paradigm is that we can engineer our many-body system. It's approximately very well isolated. And then we can artificially label a subregion as A, and think of that as our subsystem of interest, and then let it interact with the remainder of this quantum many-body system that we're going to call B. And the intuition is that A is going to describe our local subsystem, and B is going to serve as the heat bath that's going to allow this relaxation to equilibrium. And the point of view is that the quantum system should be able to serve as its own heat bath, and we can really test this experimentally. Okay, so to do that, typically what one does is, because the heat bath in an ideal sort of in the conventional thermalization setting is something inaccessible. It may be phonons, or it may be radiation into the vacuum, or any kind of exposure to an environment that we don't directly control. In these experiments, what one does typically is one ignores these degrees of freedom in B. We collect data, and then we restrict our attention onto the data coming from A. And we try to diagnose the equilibration of our reduced density matrix. That's basically like a marginal in a classical sense, where we're discarding information from part of our system and focusing on the marginal description of the subsystem of interest. However, this is a kind of arbitrary choice, a bit artificial. It's something we do to emulate something that we think happens in nature, but in reality, in a modern quantum simulator experiment, we have this incredibly powerful access to the system. For example, we can image the occupation number of every single site in an optical lattice and get this beautiful data about not just the subsystem we care about, but everything else as well, okay? And so this choice of discarding the data on B is quite artificial, and really we can think about what happens if we retain the data and really try to look for correlations, or in particular for conditional behavior of subsystem A given some measurement outcome on B. Okay, so it's a different point of view that really becomes enabled by these contemporary quantum technologies, and I think it's a really, really rich sort of source of data that is still a little bit underexplored. Okay, so lately people are really starting to pay attention, but I think there's much more to learn. Okay, so more precisely, a theoretical construction that was put forth in these very interesting seminal papers here by Sun, by Robert, and others a couple of years ago, is this concept of the projected ensemble. Okay, what this is a distribution of post-measurement quantum states on the subsystem of interest, conditioned on measurement outcomes on the remainder of the system. Okay. So the setting we have in mind is that there is this quantum many-body state, psi, on this composite system A and B. We perform projective measurements on B in some basis of our choice. This could be a natural basis, like the occupation number of our sites of the optical lattice, for instance, or it could be anything else that we have sort of experimental access to. And this gives us two things. It gives this classical measurement outcome Z, and then it gives us this conditional quantum state on the remaining subsystem A. And together, these two things form an ensemble. In particular, there is a probability associated to this label Z that is just the Born rule probability of this particular measurement outcome on the bath. And then there is this conditional post-measurement state that's defined in this way with a projector on the particular measurement outcome, hence projected ensemble. Okay. So what this is, again, is a distribution of probability on the Hilbert space of the subsystem A. And a sort of natural property that this distribution has is its first moment. We can look at the average of all of these possible states we get, and if we write it out in this way, we have to always average the projectors on the states, take this stochastic mixture. What this is, you might recognize as the partial trace of the bath B. We're just summing over all the possible states we get with the appropriate weights in order to reproduce the partial trace. So this is none other than the reduced density matrix. Okay. So we've defined a probability distribution whose first moment has this identification with the reduced density matrix. And so we know that at late times in dynamics, this object, so the first moment of this ensemble, should achieve equilibrium. And so the natural question to ask is, does the ensemble as a whole achieve some equilibrium? Does it have some universal behavior at late times? And this question was really prompted actually by an experiment in Manuel Anders's lab at Caltech that was looking at snapshots of this Rydberg atom array and noticed some interesting universality arising in conditional B-string probabilities. Okay, so I won't spend too much time going into details on this, but there is this experimental histogram here. What you can see is that this quantity being plotted is a conditional probability. Probability of something happening on A, conditional on some measurement outcome on B. Okay, and these kinds of conditional observables reveal some unexpected universal behavior. It's unexpected because the evolution that's happening here is whichever kind of specific Hamiltonian dynamics of that Rydberg atom simulator for a specific amount of time, and there's no particular reason that should be random inherently, just some fixed Hamiltonian. But nonetheless, we get this emergent randomness when we look at this conditional data. And so in the years since, this has kind of started this line of research on this concept now known as deep thermalization, which we can formalize in this way. We can at least kind of qualitatively define in this way. we can say that a system or a dynamics achieves deep thermalization if at late times, so if we have this time evolution operator and we allow time to flow to sufficiently late values, and then we construct this projected ensemble. Okay, so we interrupt our evolution at some time t, we measure part of the system, we look at what happens on the subsystem of interest. If this ensemble achieves a universal behavior at late times, then the system deeply thermalizes, if you will. Okay. So what is the physical meaning of this? What do we, why would this be a definition that one might be interested in giving? Well, the idea is that, as we said, the first moment of the ensemble, which is what describes all the expectation values of observables averaged over these possible measurement outcomes, is described by the reduced density matrix. And so this is something that we know in typical thermalizing dynamics should achieve equilibrium. However, there's much more data in this ensemble beyond the first moment. There's data about all higher statistical moments, and in particular, all of the possible conditional post-measurement states in the Hilbert space of our subsystem. And we can visualize these as points in the Hilbert space. Okay, I'm qualitatively sketching it here as a sphere. Of course, it's a high-dimensional space, but for visual purposes. And all of these dots are possible post-measurement states that get generated when I measure part of the system. The first moment will be the center of mass of this distribution. So I look at all my points, I look at sort of weight them appropriately with their probability, and I have a certain center of mass. That point describes my reduced density matrix. And the idea is that I might have achieved sort of conventional thermal equilibrium when my density matrix reaches its equilibrium point, for instance, the center of my Bloch sphere, so an infinite temperature state. But this equilibrium might arise from many, many different underlying distributions, some of them more random than others. Okay? So I might be at infinite temperature equilibrium according to the density matrix, even if all of my projected states are secretly coalescing in some particular regions of Hilbert space that are maybe low complexity or not very random or very simple, right? Or I might get the infinite temperature density matrix out of averaging uniformly random states across the whole Hilbert space. The idea is that these two things are somehow very different and we would like to capture this different behavior, and this is precisely what we mean by deep thermalization. So ideally, the amount of randomness or amount of sort of uniformity in these distributions should capture some stronger notion of equilibration. Oops. And the conjecture is that for what these ultimate distributions should be is that they should be as random as possible, obeying the relevant constraints. Okay, so this is a general principle of thermodynamics that says that entropy, a suitable notion of entropy, should be maximized. Okay, so things should become as random as they're allowed to be. Okay, and in the simplest setting of dynamics that we often care about, which is, for example, random circuits, there are no conservation laws, no conserved energy, no conserved charges, then any point of Hilbert space is essentially as good as any other. There's no particular reason to prefer some direction versus another. And then we would conjecture that the universal distribution for these post-measurement states should be the hard distribution. Okay, that's at least a natural conjecture that was put forward in some of these early papers and then verified with sort of increasing sophistication in a few following works. So on this topic, in collaboration with Wenwei Ho, who was a postdoc fellow at Stanford, now is at National University of Singapore, we've had a few works over the years. In trying to analyze new phenomena, what physicists often do is they sort of, when they don't know what else to try, they go to either one dimension or infinite dimension. These are extremes that are often kind of convenient and helpful to think about things. And so that's exactly what we did. We first analyzed the problem in one-dimensional systems modeled by random circuits. And then we moved to sort of random matrix settings with all-to-all interactions and sort of some large random matrices that we can treat analytically. Okay, so in the 1D setting, we focused on some models, sort of starting from a model of maximally chaotic dynamic that was introduced by Tomasz and others, that was known to achieve chaos in sort of the most efficient way. We were able to show that the projected ensemble in this maximally chaotic circuit is somehow able to transfer the randomness from these measurement outcomes in the space direction in a maximally sort of dissipationless manner. So all of this randomness flows through this one-dimensional sort of wire and arrives and contributes to these post-measurement states so that we have maximal randomness as early as possible. As soon as regular thermalization is established, we also have the collapse of all of the higher moments immediately. However, in general types of dynamics, instead, where this fine-tuned condition is violated, we don't have this kind of maximal chaos condition, there emerges a length scale that controls this flow of information from these measurement outcomes onto our subsystem of interest that makes it so that at some fixed time, the amount of information, the amount of randomness in these post-measurement wave functions is somewhat limited. And this enables us to establish some limits on time scales for this equilibration. And then on the other hand, when we focus on random matrix type models, we took the simplest possible model that has some notion of locality. So we have a local subsystem of interest. There is a very, very large bath that's being taken to infinity. It's like the outside world. And our subsystem of interest is talking to the outside world through the intermediation of one single bottleneck. So we have basically 3 qubits whose dimensions we can tune, sorry, qubits of whose dimensions we can tune. And by doing that, we can somehow analytically control these averages over random unitaries, and we can establish that this phenomenon indeed happens, and we can say something about the time scales, these 2 extremes. Okay. But today I want to focus on a more recent work that I think is very interesting, where we enrich this structure. Okay, we go beyond this case of no conservation laws, where what happens is just maximum randomness, and we start to see more structure. Okay, so what we wanted to do was a sort of baby step towards Hamiltonian dynamics, where there is a conservation law. Okay, there is a conserved energy in the system. However, that's often not so easily tractable because Hamiltonians are complicated. They have non-commuting terms and so on. So it's easier often to think about systems that are modeled by random circuits, but these random circuits have a local conserved quantity. And so this is achieved for, in the easiest case, by U1 symmetry. There's an on-site U1 symmetry. It has an associated conserved charge, and we can study how that affects the phenomenon of thermalization. We know, of course, that these conserved quantities have an important effect on thermalization. They induce these various Lagrange multipliers like temperature, chemical potentials, and so on that affect the limiting ensembles for the density matrix. But it's not at all obvious what that does to these overall statistical ensembles that should arise from measurements. Okay, so what we do again is we take models of dynamics that are these quantum circuits with a U1 symmetry. We feed them some input state with some kind of distribution of charge, and then we ask what happens upon measuring part of this system. And what we find is actually quite rich and interesting phenomenology. So by focusing on this particular setting with random circuits, we are able to do much of these calculations analytically in a non-rigorous but sort of reasonably trustworthy way, I would say. Okay, and then we can verify the results by mathematics, and we find good agreement. But the qualitative phenomenology we find is very interesting, and it depends on primarily 2 things. One is the distribution of charge in the input states. Okay, so in the standard case of thermal equilibrium with a conservation law, there is a 1 Lagrange multiplier, like temperature for energy, chemical potential for particle number, and so on. So the system retains memory of only one thing, only the average of whichever conserved quantity is fed into it. But in these cases, our universal ensembles that arise retain memory about much more than that, not just the average, but potentially all the higher moments of this distribution of the input conserved quantity. And secondly, the distribution depends quite strongly on the choice of the final measurement basis. Okay, this didn't matter at all in the case without conservation laws, because then any direction was as good as any other. So there's absolutely no dependence. But in this case, we are envisioning a situation in which, for example, the Z component of our spin represents a conserved density. So the conserved quantity might be total Z magnetization. And then measuring these qubits in the computational basis has a very, very different effect from measuring them in a perpendicular basis. Okay. The idea qualitatively is that we can have measurements that do or don't reveal the local charge density. And this, as you can see, has a significant effect. So in this case here, we are measuring in a basis that doesn't reveal anything about the charge density, for example, the X basis, if the charge density is sigma Z. And in this case, we have our input state that has some kind of profile of charge. This gets quickly scrambled by the dynamics, becomes uniform, but there are still quantum fluctuations. And then the measurements say nothing about what the charge was in the degrees of freedom we measured. And this is compatible with having a single distribution of post-measurement states on the remaining qubits, just like we had in the case without conservation laws, at least in principle. But on the other hand, when we measure exactly the conserved density, what we find is that we exactly reveal how many charges we have in this bath, how many particles, how many holes, if you will. And in any given run of the experiment, this will give us a different result. And the subsystem that we left unmeasured has to compensate for this value of charge. If in a given run of the experiment, we observe, for instance, an abnormally large amount of charge on the bath, the subsystem will have to compensate by having abnormally low charge. Okay, so in any given run of the experiment, we expect to draw a sample from different parts of the Hilbert space that are compatible with information that we revealed about the conserved quantity. Okay, so this is kind of the qualitative intuition, and then we make this sharp again by a sort of series of analytical calculation and numerical tests. And we have a whole zoo of possible ensembles that emerge as a function of what we measure. So again, a maximally charge-revealing basis or a charge non-revealing basis, defined based on the direction of our conserved charge density, which is Z. And also the possible input states and their charge distributions. Okay, so we can feed basically microcanonical states with a well-defined value of charge, or canonical states with some well-defined chemical potential but fluctuating charge, or we can feed in whatever we want. Okay, some unspecified distribution of the conserved quantity. And as a function of these choices, we get various possible answers. In some cases, we still obtain the hard distribution as if there was no symmetry at all, no constraint at all. In some cases, we find an interesting deformation of the hard distribution that's known as the Scrooge ensemble. Okay, Scrooge is the Disney character that's known for being very stingy. This was named like this, not by us, but in older 90s literature, as the ensemble that's extremal in terms of accessible information. It's an ensemble that is as stingy as possible with the amount of information that it reveals to measurement. And it's defined as a sort of distortion of the hard measure by some density matrix. In this case, the reduced density matrix of our subsystem that need not be maximally mixed. Okay, so this remembers basically the average charge or the chemical potential, but nothing more than that. And then finally, further looking at general distributions, we obtain this ensemble known as the generalized Scrooge ensemble. That's a mixture of several different Scrooge ensembles, basically. And this is interestingly sensitive to the entire charge distribution of the input state, not just the chemical potential, but all possible values of the charge that are fed in superposition. Interestingly, this was recently found in the energy conserving case by this very nice paper by Summon and collaborators in the case of Hamiltonian dynamics, where instead of a charge, we have a conserved energy. And there are some important differences between our case and their case, but still there is this very, very interesting correspondence that emerges to very different tools. Okay, so last thing I want to mention about this is that there is, this might look like a zoo of random sort of individual instances of things that happen, but actually there is some underlying principle that is very, very interesting and points to some universality. It says that the limiting ensembles that we obtain in these cases depend only on the amount of information, type of information that is revealed by the measurements about our conserved quantity. In particular, there are two different and inequivalent ways of learning nothing about the charge of our subsystem. Okay, the first way is obvious. We just measure the charge, we measure the system in a basis that is orthogonal to charge. Okay, so if charge is in the z direction, we measure the x direction, tells us absolutely nothing about the local charge density. And so unsurprisingly, these measurements are charge non-revealing, we get some kind of behavior. Interestingly, there is another case where the same complete lack of knowledge arises. And this is the case in which we measure in a basis that is nominally charge revealing. So we should learn the charge because we're measuring some density. However, the input state has a specially chosen charge distribution that is equilibrium. That is defined like this. So the probability of having some charge Q is proportional to this exponential here. So this is, you might recognize from statistical mechanics, there is a fugacity e to the beta mu, and then there is the value of charge. And this particular distribution factors into uncorrelated distributions for the charge on subsystem A and subsystem B. Okay, you can see it here. And so even though we are nominally learning everything about the charge on subsystem B, this tells us absolutely nothing about the charge on A, because the two distributions are uncorrelated. And so remarkably, in these two very different cases, so microscopically very different things are happening, the derivations we do are very different because of this, but we still uncover the same universal behaviors. So this points to some underlying universality about the nature or the principle governing these late time projected ensembles. So I just want to leave it at that for deep thermalization. I want to just point to some sort of open questions and directions for future work that go beyond what I discussed here. In particular, it's interesting to ask about non-abelian symmetry, going beyond the U1 case that I talked about, and similarly more complicated symmetries that are not on site. For example, translations, rotations, point group symmetries, and how those might affect this stronger form of equilibration. And even in our case, we had to restrict to these maximally revealing measurements in the Z basis and maximally non-revealing measurements in the X and Y basis. But what happens for intermediate measurements is already kind of a little bit less clear. The technicalities of it get out of hand very quickly, so we can't analytically answer this question, but it would be a very interesting direction to try and answer. But, so if there are questions at this point, before I start the second part, perhaps this is a good time.
I guess it's quick. Should I just think of the generalized Scrooge ensemble as being like the diagonal ensemble, but for charge?
Not necessarily. So we do have an ensemble that is more obviously interpretable as diagonal. It's this case here we call direct sum. That's the case where you feed in a state of a sharp charge. So there is a well-defined Q. You measure a charge revealing basis on B, so you learn a well-defined QB. So that uniquely points to a QA. Okay, you know Q, you know QB, you know QA. And then you get a hard state in the relevant sector. So maybe that's what you mean by diagonal.
Well, I would have called that like microcanonical. Right? Diagonal, I mean like dephased, right?
Okay, then in this case, I would say no. There is always coherence in these post-measurement states that you obtain in general. So it is really a bit richer than that.
So another case where I might imagine I learn nothing is if I take my initial state to be a product state in the X basis or something. So that's also the same as these other two cases?
Yeah, so a product state in the X basis will be equilibrium with beta mu equals to 0, if you think about the distribution. And so it indeed falls in this case that gives rise to the Haar ensemble, basically whatever you measure. You never learn anything. There's nothing to be learned, I guess.
So you mentioned that in the charge revealing case, you're sensitive to the whole distribution, not just the zero mode. But do you have to track how this distribution evolves in time, or is it really just the initial distribution?
It's conserved, yeah. So we're assuming that the unitary part of dynamics is always charge conserving. So all the moments of the distribution are constants of motion.
Oh, I see.
So maybe if you have more questions, you can ask again at the end. All right. Excellent. So for the second part of the talk, I want to move on to this concept of pseudo-thermalization that is in some sense the opposite of what I just talked about, which was a strong version of thermalization. Okay, so this is a bit more like the Diet Coke of thermalization, in the sense that, what is Diet Coke? It's an attempt at emulating some phenomenon, in this case, the refreshing taste of Coca-Cola, okay, without the key ingredient, which is sugar. Okay, so here in this analogy, Coke is thermalization and sugar is entanglement. Okay, so we're asking how much can we replicate, okay, about thermalization with as little entanglement as possible. And the technical ingredients that go into this, of course, are these concepts of pseudoentanglement and pseudorandomness that we just heard in the previous few talks. Okay. So just to quickly reintroduce or set the stage for this, I want to think about entanglement, but really in the many-body case. Okay, so an extensive thermodynamically large system. We know that random state of a many-body system has this page curve behavior with a volume law scaling up to half the system size and then a sort of correspondingly downward slope. This kind of thing can be measured, but only as long as you have some small number of qubits. Then the complexity of it rapidly becomes kind of problematic. So if I'm really thinking about a thermodynamic limit for n, this is essentially a mountain of complexity that we have to climb as experimentalists, okay? I'm not an experimentalist, but putting myself in their shoes. You can imagine trying to hike up this mountain, and as long as you're looking at sufficiently small fractions of your many-body system, you have tools that work for measuring this entanglement entropy. For example, the swap test, if you have two copies, or classical shallow tomography, or various other tools that work efficiently as long as the system you're looking at is scaling no faster than logarithmic in sort of global problem size. Beyond this point, it's not clear because any of these off-the-shelf tools don't really work anymore. So it's possible that you have a special case where you can do something more clever, like a stabilizer state or fermionic Gaussian states or something of that nature. But in general, it's not so clear whether this region of the page curve is something that you can really probe. Okay, so are extensive amounts of entanglement, sort of in this thermodynamic limit, are they fundamentally measurable, feelable, okay, knowable? Or can they be hidden? Can they be spoofed by suitable quantum states? Okay. So this question was answered really dramatically in this paper by all of these authors, including Adam here, that introduced the concept of quantum pseudoentanglement. Okay, this is a property of quantum state ensembles. Okay, so again, distributions of probability over the Hilbert space that are defined by two seemingly contradictory properties. One property is that they have low entanglement. In particular, we will want the entanglement to be sub-volume law, so asymptotically not page. And at the same time, they are pseudorandom in the sense that they are efficiently preparable, yet not efficiently distinguishable from hard random states. Okay, this is everything we just heard for unitaries. Now we are only applying it to states, but it's closely related. So the existence of states that have this property has some striking consequences, okay, because it implies that it is possible to hide very large, extensive amounts of entanglement away from any observer whose resources are limited by a polynomial scaling. And by resources, we always mean everything from time to classical or quantum memory and anything as we can imagine that would define an experiment as being efficient. Okay, so any efficient experiment you can do in the worst case scenario still won't be able to tell you about the true nature of many-body entanglement. Okay. So zeroing in a little more precisely about this idea of sort of efficiently distinguishing these states from random, the definition looks like this. Okay, so this is the concept of computational indistinguishability. The idea is that given any polynomial number of copies of the state, okay, here, sorry, I'm using the capital N as the number of qubits. I know that in previous talks this was the Hilbert space dimension. Sorry for the confusion. So for any number of copies M that is polynomial in system size, and again, this limitation represents our limited quantum memory. We have some number of quantum computers we store these states that can't be huge, you know. And for any possible efficient quantum algorithm A, so this is some kind of quantum circuit we run, and then we make some projective measurements or some kind of binary observation of our system. For any such algorithm, the difference in outcomes between M copies of our pseudo-entangled states versus M copies of a hard state cannot be too large. And in particular, it has to be asymptotically smaller than inverse polynomial. So that again, in polynomial time, you can only take polynomially many shots of this experiment, and we won't be able to resolve this very tiny discrepancy. Okay, so it doesn't matter how clever you are, nothing you do will ever be able to tell you whether the states are random or not. Okay, so this is the proper definition. I have to give a disclaimer that in our work, we, again, kind of to make our lives a little easier and get something computable, we relax this assumption about the efficient algorithm. We allow for the optimal distinguisher between these states, which gives us this trace distance, which is a computable thing. So in jargon, this will be really an information theoretic distinguishability rather than computational. Okay, but yes?
I think someone might have asked a question like this in the previous talk, but I don't remember the answer. So what is the strong difference between this concept and the unitary design?
This one here is a epsilon approximate M design. Yeah, this is that definition. Thanks. Sorry, this is a state though. This is a state design, not a unitary design. State design.
Okay.
Yeah.
This is a design for like some super polynomial M though, because you're specifying the construction and saying it's true for all polynomials, right?
Yes.
Like as a design, it would have to be M bigger than any one of them.
Right, right. Yeah, so this line here describes an M design, but then I'm also demanding it for every possible polynomial M. So this is very powerful. Okay? It's maybe a little overkill, but again, it's for practical reasons. Okay, it would be a nice improvement on this work to really focus on the computational version of diffusion. Okay, so I've given this definition, which is really impressive and seemingly contradictory. It's not at all obvious that these states exist, but luckily they were constructed by, again, these authors, in particular, Adam Bulan's group here at Stanford. And a really simple construction of these pseudoentangled states is given by the so-called subset states. Okay, so what are they? Well, as the name suggests, they're defined out of subsets of something. This something is the computational basis. And so the idea is we take a certain number of elements of the computational basis, we write them in coherent superposition like this, we normalize, all the amplitudes are exactly the same. And so this defines a quantum state psi of S, that's our subset state, based on that subset S. All of these states are not orthogonal to each other. It's a very overcomplete set. As an example here, for just 3 qubits, we can picture the computational basis as a cube with the vertices labeled by 3-bit strings. And a subset state would be obtained by, for example, coloring some of the vertices in red. And in this example here, we have this particular subset state written out here. So imagine this in a many-body setting now. Okay, so some very high-dimensional hypercube. So in these states, the entanglement is capped by this amount, log of the cardinality of the subset. This follows from the Schmidt decomposition of this state. You can easily convince yourself that the entanglement is this or less, just from the low number of states in superposition here. And importantly, this amount of entanglement can be tuned if we just choose a cardinality of the subset according to what we want. And so if we pick this cardinality to be a function of system size that scales in this particular intermediate, middle ground between polynomial and exponential, then this ensemble here is indeed pseudoentangled. Okay, so as we choose the subset uniformly at random out of all possible subsets of this cardinality, that distribution is pseudoentangled. Okay, this is, I think, quite surprising. All right, I should say in the meantime, okay, this was 2023, but in the meantime, there's been all of these very exciting new constructions of pseudorandom unitaries that if you apply them to an arbitrary input state, will give you, if you apply to an arbitrary product state, will give you a pseudoentangled state. So now there are many more flexible constructions of pseudoentanglement as well. So the idea of our work is to sort of test this link between entanglement and thermalization, because in any sort of reasonable normal case we can think about, the two go hand in hand. Okay, so we can have either systems that maximize entanglement over the course of dynamics and accordingly exhibit thermal behavior, or we can have systems that for various reasons face some obstruction to entanglement growth, slow entanglement growth, or saturate to some abnormally low entanglement. But typically this goes, this implies some very obvious signature of non-thermal behavior. For example, local expectation values won't relax. Okay, so you won't need to go and look at very sophisticated entanglement measures. You'll just see something staring you in the face that says that these systems are not at all approaching equilibrium. Okay, so it's interesting to ask whether these two things, okay, entanglement and thermal equilibrium, have to strictly go hand in hand, or how much can we sort of stress this connection? Okay, how much can we separate the two? The idea we pursue here is, what if we had models of quantum dynamics that equilibrated to pseudo-entangled state distributions instead of sort of the typical random-like states with high entanglement that we normally encounter? If this thing is possible, then we would have dynamics that reproduces all the efficiently testable predictions of equilibrium, in particular infinite temperature equilibrium, while at the same time evading this sort of typical maximum entropy principle for entanglement, which will be a bit counterintuitive. Okay. And so to that end, we need to define some models of dynamics that reasonably, we can reasonably hope will equilibrate to these pseudo-entangled state ensembles. Okay, again, the ensemble we have in mind is the subset state ensemble. And a natural way of ensuring that we equilibrate to that ensemble is to start there and never leave. Okay, that way we can be sure to, we have a good shot of equilibrating to subset states. And so the models we consider are simply random reversible circuits, which we've heard about before in Jonas's talk. Okay, so these are circuits that take in a computational basis state and output a different, potentially different computational basis state, but they never create superpositions. In other words, they act like classical circuits on these classical inputs. Unitarity implies that these 2-bit strings, so Z and Z prime, need to be in one-to-one correspondence, so hence the reversibility. So these are really permutations of the computational basis. And we can visualize their action on a subset state in this manner. Okay, so again, imagine our 3-bit example, which is a cube, and we've colored some of the sites that represent our subset state. When we act with one of these reversible classical gates, what they do is they permute the vertices of this cube. Okay, so in particular, as an example, we can act with this Toffoli gate. Again, we've seen it before in the talk by Jonas. This is just a reversible AND gate. We take 2 of the bits, we take their AND, and we add it modulo 2 to the remaining bit here. Okay, so this is a reversible gate. And what it does is it takes these 2 bits that have a 1 on both the first and the third place, and it exchanges them. Okay, it adds 1 to the second bit modulo 2. So what this amounts to is this exchange of these two vertices of the cube. And you can see very easily that the number of red dots doesn't change in this process. Okay, we're only moving things around. We're not creating or destroying any red dots in the process. So what this means is that these reversible classical gates will transform a subset state into another subset state with the same cardinality of the subset. Okay, so importantly, these gates can create entanglement. Okay, can move entanglement around, but they cannot grow it past this bound that we've established based on the cardinality of the subset. Okay, so we are guaranteed that if we start, if we set this parameter sufficiently low, we won't equilibrate to a page state. Okay, we can have this cutoff that's always respected. And then what remains then is sort of understanding how this dynamics plays out in time. Okay, so imagine now we're drawing these random reversible gates from some ensemble and dropping them down on random places in our system. What it does, each one of these gates will alter our subset. Okay, and so if we have this sequence of random gates, this amounts to a random temporal sequence of these subsets versus time. Okay, so it's a discrete Markov process. We're moving in some suitable space of subsets. These are catastrophically large spaces. It's a combinatorial problem. These quickly grow explosively and get out of hand very quickly. Here I'm showing, for example, a space of states for only 3 qubits, and I'm showing subsets of cardinality 1, 2, and 3. Okay, so cardinality 1 means it's only bit strings. Cardinality 2 means it's pairs of bit strings. Cardinality 3, it's triplets of bit string, and so on and so forth. And these connections here are Toffoli gates, basically, that can connect to these subsets to each other. And you can see that the sort of the connectivity of these graphs gets very intricate quickly. Nevertheless, okay, sorry, I should mention these initial subset state can be very simple. For example, it can be a computational basis state tensored with some plus states. Okay, so if you expand this out in the computational basis, you'll see that you get a subset state that's very special, very correlated subset state. And then as the dynamics plays out, you will explore these spaces of subsets sort of in some ergodic way, and eventually equilibrate to a uniform distribution over these subsets. And once that happens, you by definition get a random subset state, which is a pseudoentangled state ensemble. Okay, so this phenomenon, this equilibration to pseudoentangled states, is what we call pseudothermalization. And what's really fun about, once we do some math in order to map this quantum distinguishability problem onto a classical Markov chain, we can now resort to some known facts about Markov chains on some interesting spaces. In particular, there is this literature from math about shuffling decks of cards. Okay, so these are complicated random walks on large spaces, in particular groups of permutations on many elements. And these Markov chains are characterized by a sudden equilibration. Okay, so unlike maybe diffusion in 1D or things that we are more familiar with in physics, these kinds of Markov chains equilibrate in a sudden way where we are very far from equilibrium for a long time and then abruptly kind of collapse to uniformity. For example, for a deck of 52 cards with the usual riffle shuffle, you need 6 shuffles to get close to equilibrium. Okay, so in our problem now, the role of the deck of cards is played by the computational basis. Okay, so there's 2 to the n cards. The subset state is like drawing a hand from the deck. Okay, so the cardinality of the subset is how many cards you've chosen to draw. And then our elementary Toffoli gates or classical reversible gates are correspond to these elementary shuffling moves. Okay, so by increasingly applying these gates, you shuffle the deck better and better, and eventually these hands of cards you draw become very random looking, and then you are pseudoentangled. Okay, so again, the existence of this cutoff phenomenon in these processes implies a very interesting sort of dynamical transition in distinguishability that arises in these dynamics that says that up to some time that we can characterize, we can bound, there is something we can look at in order to distinguish these states from random states. There is something that can efficiently distinguish them with a you know, any finite or polynomial number of copies m. And then past that time, quite abruptly, these states look random for all intents and purposes. Okay? Even though their entanglement never grew past that cap that we set at the beginning. Okay, so I'm approaching the end of my time, so I just want to, okay, so I'm going to flash the circuit model, which again is just we're dropping down these Toffoli-like gates on quantum states that are trivial on most of the system, and then feature either an initial pseudoentangled ensemble on a small system or even a product state. And then we see how the pseudoentanglement spreads or gets generated from scratch. A point that's interesting is that we need these range 3 gates, as Jonas also mentioned. 2-qubit classical gates are too simple. They're just CNOTs. They're not magic. We cannot get pseudoentanglement from those. So this is in some sense a minimal model. And then an interesting sort of fun fact is that we reported, once you map the problem onto this mixing of these reversible classical circuits, there is now all of this literature you can look at for the mixing times of these processes. And so we had to go back and look at these works from the 90s and 2000s. And then within a couple months of posting this paper, the state of the art sort of collapsed down to much stronger bounds, very short order, which was a fun surprise. Anyway, we can place bounds on the time taken to achieve this indistinguishability in terms of the number of copies and the system size. Just not going to say anymore. I just want to comment briefly on the sort of qualitative implications of this statement, which is that we have an initial state that's not very quantum. It's disentangled. It features a bit of coherence in the sense of superposition, but not very much. Only a vanishing fraction of the system has coherence. We've evolved with classical gates that are local, so really kind of like a classical cellular automaton, similar to Rule 54. And at late times, this becomes indistinguishable from the most quantum, most highly entangled, most magic states you can imagine, which I think is surprising. I would not have believed it before sort of doing this work. Okay, and this, in echoing something that Sagar suggested the other day, depending on how paranoid you want to be, okay, you might think that nature is perhaps trying to trick you and that maybe the universe is less quantum than you think. And this sort of gives you the slightly unsettling suspicion that maybe you would not be able to find out if that was the case. All right, I'm going to stop here on this. I just want to mention in passing these works on holography that were mentioned before. I can tell you more in the panel if you're interested. Okay, so we've introduced this idea of pseudo-thermalization that is about emulating all the efficiently verifiable features of infinite temperature equilibrium with limited entanglement. In the process, we uncover these cutoff phenomena, these connections to these sudden equilibration of Markov chains. And I think there are many interesting directions to pursue in future work. Some of the same ideas that Robert just pointed to, so the hardness of learning and verifying complex quantum processes in dynamics. Also, as I was saying, we've resorted to this stronger information theoretic notion, okay, of pseudorandomness, but it would be desirable to find models that give rise to this computational pseudorandomness. And here the tricky part is make them physically reasonable. Okay, we know that this is possible on a sort of computer science level, but finding a reasonable physical model with the flavor of thermalization that does this, I think, is an interesting future direction. And also, it's interesting now that we have more models of pseudoentanglement to try and find more applications to many-body physics. For example, not just in late-time states, but also in eigenstates of Hamiltonians or other interesting states that might arise. I want to close with a couple of shameless advertisements. One is that we are hiring 2 postdocs at UT Austin in collaboration with Scott Aronson and Nick Hunter-Jones. So broadly in quantum information theory, one in physics, one in computer science. Please, feel free to apply here. If you know anyone who might be interested, let them know. The deadline is in December. We've got a growing effort in quantum information. We've got great tacos. Feel free to join us. Second shameless advertisement, if any of what I talked about, or if you're here, presumably you find it interesting, there is going to be a KITP program next fall, September, October, on very much these kinds of topics of pseudorandomness, dynamics, thermalization, and so on. That should be a very fun time to be at KITP. There's also another exciting program at the same time, so I would encourage you to apply. And with this, I'm really gonna close. Okay, so thank you for your attention.
Questions?
So is it possible to do this on some system with conservation law, with conserved energy, like something like pseudo keep state?
Yes, I think that is a super interesting direction. I think maybe I didn't mention it, but it definitely is. It's not so easy because I think the obstruction is that we don't yet have models of pseudoentanglement that are amenable to that kind of structure. So first thing I should say, I guess, is when we did this work, there was basically only that model of pseudoentanglement, and it was permutationally symmetric, so no geometry even. So the only thing you could reasonably hope to capture was this in temperature behavior. Now we have a few more. Okay, we have like shadow circuits and things that have a little bit more geometry to them. So I think that there's hope of building in more structure, but it's not so easy how to build in, for example, conservation laws in a way that preserves preserves pseudorandomness and even identifies the correct notion of pseudorandomness of what you want to emulate. I think it's an interesting direction. I don't have anything very intelligent to say.
Hi. So if you were to slightly perturb away from these pseudo-random unitaries, would you expect your system to start thermalizing more generically immediately, or would you expect maybe there's some finite region where this type of weird thermalization or pseudo-thermalization behavior is stable?
Yeah. So that's a very natural question, I think. Yeah. And what I didn't test this, okay, but what I expect is that we get some maybe Fermi's golden rule or something like that, right? You have some small perturbation away from these reversible classical gates. They will start generating additional coherence and breaking this bound on the Schmidt rank. But that process will be, you'll get a holistic growth of entanglement, I suspect, with a slope that's determined by the strength of the perturbation. So as long as your perturbation is very weak, you will still have the pseudo-thermalization before the true thermalization kicks in, and so you'll still have a temporal window in which I think this is relevant.
Can you say a bit more about the last thing you had about the eigenstates? Like, can you have some kind of like pseudo ETH or something?
Right. So I think that's like another very natural thing to think about. And again, I don't have anything super concrete to say, but there are some sort of there are some fingerprints of locality in eigenstates that maybe Xiaoliang and others have worked on that tell you that they can't just naively be pseudorandom in the same way that these pseudorandom states are. Okay, but again, kind of echoing the point about conservation laws, the question becomes what is the relevant thing to try and mimic? Okay, presumably not hard random states, but something that has some locality. But yeah, so and another I think interesting point is there are some atypical phenomena that can happen in an otherwise typical spectrum, like quantum scars. Can you hide something like that in an otherwise boring spectrum? I think that's very interesting.
It seems like you could also add random phases to your random permutations if you want to and still preserve the low entanglement. Did you consider, like, does that change, I don't know, how quickly it mixes and things like that?
Right. So that's a very good point. And indeed, I think that's how we started, because if we go back to subset states, the first construction actually in the 2022 paper had phases, right? So we were thinking initially about putting in phases in order to build in not just the random permutation, but also random phases. That just turned out to be quite tricky mathematically we're bounding some trace distances at the end of the day. And without the random phases, it's very tricky. So we were very happy when they later posted the version without the phases. That turns out to be easier. But yes, there's no reason why that shouldn't work. If you just put in binary phase gates, you start building up these random plus and minus one signs, and there's no reason that they shouldn't be coming from random at late times. Just a bit harder to sort of.
Oh, yeah, definitely, almost certainly would.
Yeah.
Like, I'm just wondering if it changes the
if it changes, it doesn't affect the dynamics of subsets. It's only, as you know, permutations and phases basically commute. So it doesn't change that equilibration of subsets. It might conceivably delay like the. Yeah, I don't want to say anything that I'm not confident about, but yeah.
I think you mentioned that you couldn't use two local gates because you needed some magic present. Well, could you elaborate a little bit more on the role of magic, and is there some sense in which you need like a certain amount of it present in your in your circuit? Is below a certain threshold, does this vanish, or do you just need it to be present at all?
Right. So the reason you need some magic is that stabilizerness is efficiently testable. And so if you have a stabilizer state, there's no hope that it can be pseudorandom, and just test and find out. How much magic you need was answered recently in a couple of papers. One of them had a funny title that I think I remember, Pseudoentanglement ain't cheap. So yeah, anyway, they bound how many T-gates you need to get a pseudoentangled ensemble. And it's not very many, but it's I don't remember the scaling off the top of my head. So you don't need too much magic. We have a lot of magic because all of our top follies are magic, so they're everywhere. You need less than that, but in an otherwise stabilizer circuit, I guess. And why? Sorry, what was the other part of the question? Okay, great. Yeah.
All right, if we don't have more questions, let's thank the speaker again. I think we'll come back in 30 minutes for the panel.